Okay, so last class we talked about the sunflower lemma again, and we kind of went over the high level approach towards the sunflower lemma, right? So we said we had a basic inductive proof, which is almost 60 years old, and then we tried to kind of improve it by not looking for a single set to induct on, single element to induct on, but multiple elements. But there was one twist where we kind of strengthened what we wanted to get, right? So this led to the notion of spreadness. One way to think about spreadness is, it's essentially what you have when you cannot do any more induction, right? If I can find a small set of elements where you make some progress quantitatively, you just take that out, condition on it, or go to its link and proceed. But at some point you get stuck, and that's when you have spreadness. And then we had this robust sunflower lemma, right? So even though the original sunflower lemma had no probability or anything, we were going to show a stronger statement, which we did observe implied the sunflower lemma. Okay. So today, what I want to do is basically prove the spreadness or RSL lemma. Okay. And along the way, we will look at this idea of counting by encoding. Okay. And couple of announcements. So your assignments or midterm are almost graded. They should be out today. Midterm 1 grades will be out today. Okay. And we still have time for the next one, but let me just confirm the date. Yeah, we still have 2 weeks, so it's okay. All right. Okay. And before going on, I first want to point out a couple of things that I did have wrong in the last lecture. And I'll make one change to the proof. And I'll tell you the change and why I'm doing that in a second. The first thing is, okay, so the overall approach, everything is fine, but the implications are also fine, but the attributions weren't. So okay, so this is what this paper showed. Okay. The bound that I stated is actually from a follow-up paper, which sharpened this. So, a small difference in some sense, but it's also important to be precise. So, okay, this is what the original paper showed, but then later on, people basically removed the log k term. And originally, I was just going to try and do this proof, the ALWZ proof with the log RK, which is, in some sense, I feel slightly more intuitive, okay, but gives a worse bound. But I think I'll just do the refined bound, even if it's a little bit more, instead of pulling 3 rabbits, you're pulling 4 rabbits out of the hat. Okay, and that's one difference. The other thing, yeah, so here I have almost the same bound, but I missed the R in copying the stuff. Yeah, okay. Yeah, that's the thing. So I think there's some, I missed an R in restating the lemma. But the implications are fine. The implications, everything is exactly as they should have been. Okay? All right. So just to summarize kind of the history, the original sunflower lemma, due to Erdős and Rado, showed that if I want a sunflower of size R, where the sets are of size K, you needed this to be basically R minus 1 to the K times K factorial, which is roughly RK to the K. Okay? And there's small improvements, but nothing much until ALWZ20, which gave there are some small differences, but the main thing is that the K to the K essentially became log K to the K. Okay, that's the biggest improvement, as I said. Even for R equals 3, this was a huge improvement over what was known. And then there were several papers which kind of rephrase this argument. And eventually, it came down to the better or simpler bound, which is just this. Okay, basically shaving off this log K, log RK, and then kind of this R also disappeared. Okay, cleaner bound. And I was thinking of just showing the original bound, but I think with a small, some additional work, we can show this. I'll actually show the current best state of the art bound. Okay. All right, any questions about this change in plan? I mean, the overall thing is exactly the same. We're going to make some small tweaks here and there. All right, okay. So what are the small changes that we need? Okay, so where were we? We had this lemma yesterday. Okay, so we were working with this and we said, if we have this, we do get the sunflower lemma, at least for spread sets, and then you're done because you can always reduce the spread sets by induction. Okay, and this was where we use this sort of disjoint sets, finding several W1 through WR and using the union bound. Okay, and I'm going to make a couple of changes which are small but helpful. So one way to think about this parameterization, either you talk about the size of the set you're picking up or the spreadness. Okay, what you're really interested in is the relation between the two. But in this lemma, there's also another relation which shows up in this probability of failure. Okay, so I'm going to get rid of one parameter, and it doesn't hurt. You just need to use some standard sort of Markov inequality to get the usual versions. So let me state it that way. So let me call this the new spreadness lemma. So which will say if F is S spread, where S is something, and W is a random subset, of the universe of size I'm just going to shoot for a half here. Okay, and the point is, even if you get a half, you can boost the probability. That's one way to get back the original thing, or just kind of by drawing independent samples and taking the R. or you can even just kind of use a Markov inequality to get the final conclusion. So, but you get some improvement in this bound as long as S is some C times R times log n. Different constant, but this is enough. Okay. So I'm kind of relaxing the final probability of failure, but I'm improving on the spreadness. All right. And this also, just as we saw in the last lecture, even this implies that disjoint sets in a spread family. If F is S spread, where S is bigger than some other slightly bigger constant times R times, oh, this should be K. Then F contains R disjoint set. Okay. The proof is very similar. You just have to pick, some number of disjoint sets and use the union bound appropriately. Okay. Any questions about this? Okay. So whole of today's lecture, maybe I'll say try and prove this. It's the same argument as before with some small changes because you have this probability only half. So instead of doing union bound, you have to use linearity of expectation, but it's really the similar argument. Okay. Okay. So so today the main focus is going to be to prove this lemma, the spreadness lemma. So saying if you have a spread set, then somehow if I pick a random set, I'm going to hit or contain one of the elements in my family. Okay. Again, it's helpful to keep this intuitive picture in mind. In some sense, if you think of this universe as is here, and you're drawing all kinds of random sets. If the sets are spread, we would like to say that it's hard to avoid. They're kind of spread out everywhere. Now, if I pick a large random set, it's hard to not contain a single one of them. Okay. All right. So how do we prove this? And this is where kind of we have to be very clever. And where this comes from has a completely different story from circuit lower bounds, in particular Rasborov's proof of the switching lemma. If you know what that is, that's the origin for this proof technique. But otherwise, I'm just going to talk about the proof because it's really quite ingenious, but there is a precursor in circuit lower bounds for this. Okay. Now, what do you want to say? So F is S spread. I'm just writing down what we already have. S is some R log K, and W a random set. Okay, so this is what we have. And we can either think of it, with this parameterization, or just say this is of size greater than or equal to log K by S. It's the same thing. Okay. R is, S over log K, so I get something else. All right. The two different ways to parameterize is just the same thing. Okay. Now, if you think of, let me draw a really, these are my different sets, suppose. Some are small, maybe, some are big. You can also assume all of them are the same size. It doesn't really matter. Okay. Let me just give them different shades. They could be overlapping, of course. Okay, this is S1, S2, S3, up to some number Sn. The number of sets isn't that important. We know it's a S spread family, okay? And so, this is not a Venn diagram, as I said, because the sets could be overlapping. I'm just drawing them separately to kind of measure how we make progress, okay? Now, here's the, very subtle but important conceptual idea. We're picking a random set of size this much, okay? And at the end of the day, we want to say, I cover one of these sets completely, right? And the first sort of, mental experiment we are going to do is not pick this random set at once, okay? We're going to pick this random set in phases. Why often it's difficult to measure progress in one shot, okay? We want some sort of gradual way to measure progress. What does gradual way mean? Maybe you'll say, okay, let's say I'm shooting for something, the statement like I pick W of this size, I contain a whole of some set, okay? Instead of that, what we're going to try and say is, I'm not going to pick as many elements in the first go, but I'll pick a few elements and say I make some progress towards containing one of these sets. And then I pick more elements and I make more progress. I pick more elements, then I make more progress, and so on. Okay? So what does this mean? Instead of picking W of size in one shot, I'm going to view this W as I'm going to pick W1, W2, WL, L is some C log K. Actually, let's just think of log K. The constants will be, they're all very malleable, so let's not worry about that, okay? Instead of picking one random set of this size, I'm going to pick L random sets. Okay, and the point is, if I take random sets and take their union, it's still a random set. Okay, so that's the sort of kind of self-reducibility that's implicit in picking a random set, right? I ask you to pick 100 elements from, from a universe. I can pick 50 at random and then pick 50 more from the remaining. It gives me the same exact distribution, right? So we're going to do the same thing. Instead of picking like 100 at once, I'm going to pick 10 first, 10 from the remaining, or even 10 from the whole thing. It doesn't quite matter, because as long as my set is smaller, I'm happy. Okay? So, but this allows us to measure progress in a more graded way. Okay? Instead of saying W hits everything at once, we'll say W1 gets us half the way there. W2 is going to get us half the way again. W3 is the remaining half, and so on. Okay? All right, so that's a big, that's an important sort of change in the proof that we're going to make. All right? Okay, so we'll pick this and we'll say W1 will make some progress in that there exists some set S in F such that goal. What is our goal? We want S to be contained in W. And I think this is. Okay, we want a set S which is completely contained in the family. Now, this is equivalent to saying there exists S in F such that size of S is 0. Okay, all of S is contained in W, the difference has 0 size. Okay, and instead of saying S is completely contained in W, the relaxation is going to be, we'll say half of S is contained in W1. Okay, some progress has been made. So we're going to shoot for there exists some S such that okay, S, all of the sets at size at most K. After choosing W1, we're covering, almost half of them. Okay, or at least a half. So what does this mean? Now imagine our W is some set, right? So it's some set which covers some portion here, some here. Maybe it doesn't hit S3 at all, and it covers most of S4 and so on. Okay, so W is this purple set. It hits some of these S's, some things it may not hit at all. But we're going to say that at least one of these sets is covered in half. Okay. Do you think only one set will be enough for induction to go through? Like let's say for W2, if you just find one set which are covered in half, can we restart the process and use the same argument again and say half? It seems problematic at the very least, right? Like if you have only one set, somehow the hypothesis has become much, much weaker, right? So that's exactly what we're going to try and kind of mitigate and say that not only is there a single set which I cover, but there are lots of S in F such that this happens. Okay, there are lots of S such that this happens, and then I can define some kind of good, FW1, which is all S in F such that okay, look at the good sets in which I made some progress. The first set covered half of them. And if this family is spread, I can apply the same thing again, use W2, and I will cover half of whatever is left. Okay, but we need this set, this family to be not empty, and also for it to be spread if I want to kind of use the same argument again. Okay? Make sense? Okay. I mean, this is the high level picture. So I wanted to say that. And now we can say the precise statement that we're going to show. Okay. It is set one. Yeah. So I'll just say it as an idea. Argue that okay. All right. So how do we measure this? And we have to be careful in defining this F prime. In some sense, the definition is fine, but the notion of spreadness, you have to be a little bit careful in that you have to change the distribution over F. Okay, we'll see what that means in a second. And it kind of shows up relatively naturally. Okay. So let me draw this picture again. So we have S1, we have S2, S3, so on up to Sn. Okay. And the W1, I'm going to use the letter V. So V is a random set of size C over S times size of the loop. Okay, so there is no log anymore. The log really just comes from the fact that each time we make half the progress, you have to do it log k times to cover the entire set. Okay, so that's where the log comes from. We are only going, like, this is the real deal. Okay. Now we pick this random set V, and every time we make some progress. And maybe this is not hit at all, and we have this. Okay. So let's call this S1 slash V. You have S2 slash V. This whole thing is S3 slash V, Sn slash V. Okay. Now, the original sets were all disjoint from each other. Not disjoint, distinct sets, right? You have distinct sets and they were spread. Okay. But I'm taking out, or potentially taking out, at least half of those elements, right? Maybe the first set is 1 through k over 2, and then k over 2 plus 1 up to k. The second set is 1 through k over 2 and 2k plus 1 and so on. I take out half, they could collide, right? It could be that S1 slash V and S2 slash V, they're all the same. There's nothing that prevents that from happening. And it could be problematic because if they collide and we only take one copy of it into account, we are losing count. We are losing entropy in the family that we have, right? So we're losing information in these things. In some sense, if everything is the same, we're in much better shape than we should have been. Okay, so you don't want to lose that information too. So to do that, we basically, you just imagine that this is S1 slash V. Okay, and this is S2 slash V. This whole thing is S3 slash V. And this is Sn slash V. Okay, maybe let me just draw this. Okay, I'm looking at the pieces that, I've eaten some of these sets, which is good for me because W1 covers that. But now I want the remaining W2 and so on to kind of cover these things. Okay. Cover one or maybe at least several of them. Okay. Now here, as I said, some of these sets could now collide with each other, right? Or, maybe S1 slash V is a small S1 and is contained in S2 slash V. I could have some relation like this. Maybe these two are uncomparable, but maybe I have this is something else like Si slash V, and this is contained in this guy. Okay. At the end of the day, I want to cover one of these sets, right? If I want to cover one of these sets, like, if I want to cover S2 slash V and this relation holds, I should just focus on this, right? If I cover this, I'm going to cover this. And if I cover this, I'm already done because I hit some of the one thing in the family already. Okay. So in some sense, I'm going to look at what is the minimal fragment that I need to cover. Okay. There could be a big set, there could be a small set, and this could be contained in that. This is contained, in some sense this is irrelevant. If I cover that, I'm going to cover this. And if I cover this, I already win. Okay. So I should only focus on like the minimal fragments, the minimal thing that I need to overcome to cover that one of the sets in the family. Okay. And this is a very important definition. In some sense, isolating this definition from the original proof was helpful in understanding, refining the quantitative bounds, and also extending it to other applications. Okay. So what is this minimal fragment? We'll call this minimal fragment S comma V is argmin. Okay, so I'm gonna write down the definition exactly. Okay, so what is it saying? Look at all of it. For instance, let's say I want to compute the minimal fragment of this guy, right? I have this piece. Now, among all the fragments left, one of the, whatever is the smallest contained in this, that is what I'm going to associate with it. Okay, I'm building some kind of graph which says, from now on, forget that this exists and just map it to this guy, because that's a minimal fragment. From now on, forget this guy, just map it to this. Okay, so among all the fragments, you have some containment relations. Among all the sets which are contained in it, pick the one which has the smallest size. So this should be the size. And that's what I'm going to focus on. Right? Greedily, I'm saying if I want to cover this set, I need to cover the things which are contained in it. And I only need to cover one of them, so I'm going to focus on one of the smallest sets. If there are several, just order them lexicographically and pick one. It doesn't matter. Okay. And technically, this should really be a family, but we can avoid F, avoid writing F. When it is clear from context. Okay. Any questions about the definition of minimal fragment? Being greedy, more or less, we're saying I want to cover the set S or one of the things in the family, go to the one which is contained in it, and we'll make some progress there. Okay, let's make some observations. In some sense, we are, minimal fragments are helpful because this statement is not quite true that this F prime is spread. You have to tweak the distribution, and that's what minimal fragments helps us do. Okay, all right. So what are the observations? First, we have S contained in family. V is some set. Think of it as the W1, which is random of certain size. Then okay, it's definitely contained in the set S, right? It's a piece, I'm taking this piece and then going to things which are contained in it. So the minimal fragment is contained in the original set. Okay, that is true. And okay, the next one is that these are disjoint from B. No, this is true just because these are S/V, right? Here we took out V already. So these are the fragments that are left out after taking V. Okay. The third property, which is, okay, so when can this happen? If the minimal fragment for some set is empty, are we in a good shape or bad shape? My claim is that's the thing that we are really shooting for, right? because we want some set in the family to be contained in W. And this happens if and only if there exists some set T belonging to F and T is contained in V. Okay, do you agree with this? Why, minimal fragment is empty doesn't necessarily mean that this set is empty, but there's some set which is actually empty. Some set for which the corresponding fragment is empty, which means that that set was completely contained in V, which means we already won. Okay, so one means that I found a set in my family which is contained in W1. Okay, all right. All right, so we have some basic properties of minimal fragments and the definition, and here comes the important inductive claim. The proof of this claim is, maybe if you write it down in LaTeX, it might be 1 page, but it's not going to be the easiest 1 page. Okay, it's very, very subtle. The proof has very high Kolmogorov complexity in some sense. You have to, it's easy to write down, but it's very subtle. Okay. Okay, so minimal fragments. So let's say progress in minimal fragments. All right. And so what is this saying? I have family F is S spread. And remember, all of the sets are of size at most K. And F is S spread. And V is a random set of size, for some constant C, which doesn't matter. It would basically cover C over S fraction of the elements, right? Then I'm going to first take a probability over V and then look at how many sets are bad in the sense that their minimal fragments are still big. Okay, so originally here, I wanted to say, look at all sets for which they're, I'm not covering at least a half. Okay, instead of that, the main change I'm going to make is replace this accounting with because in some sense, making progress on the set itself could be difficult, but I don't need to make progress on the set itself. I need to make progress on some of the sets, and the way I'm going to do it is to look at the minimal fragment size. Okay, so that's the subtle change. Probability over V, and then probability over S in the family. The second probability is just like a counting argument. How many sets are there in my family such that their minimal fragments are still big? And the answer is very, very few. An exponentially small fraction of them actually have their minimal fragments be big. Okay, any question about this? The statement, right? And if this happens, how would you proceed? Suppose I have this statement. How would we proceed to showing that after C log K over S, if I have a random set of size C log K over S, I would cover some set in the family. Well, I would repeat it, right? So if this happens, then idea is repeat the claim with F prime equals okay. Now this might be a collection of multi-sets, but you can just take the multi-sets and the same argument would work. You can define spreadness with respect to multi-sets too, or in other words, you can define it with respect to distributions over set families. Everything works out. Okay. So I said the twist in this sort of intuitive picture was instead of looking at S/W1, I'm looking at minimal sets being small. And then I'm going to induct on this F prime and repeat with W2. Next time it will become K over 4. After that, K over 8. At some point, it will become less than 1. And that means that your set is empty. Okay? All right. So I want to repeat this. Why do we need such a high probability? Basically, we need such a high probability statement to ensure that this F prime is spread and I can make the induction to go through, right? That's why we need such a strong statement here, because to repeat this, I need F prime to also be spread. Otherwise, I lose the hypothesis and I don't know where to start. Okay. All right. So let's work on proving this claim. And yeah, so the proof of this claim is where you use, these are uniform distributions, so I can really define something like this. Okay, let me say. Okay, let's look at all possible bad sets. Not bad sets, but bad combinations, really, right? In some sense, the experiment we are doing now is I'm picking a random set V, which is uniformly distributed over all things of certain size, and then a random element S from my family. And saying, what is the chance that when I look at the corresponding minimal fragment, that is big? Okay, I want to count, or I want the probability bound. But that's basically the same as saying that the number of such things is small, right? Because probability or V, probability or S. Let me call this Q times U just for notation. I don't have to write C over S every time. Okay, so Q equals C over S. And maybe let me put a ceiling here just to avoid any confusion. Okay, so this is a probability count, right? If I have so many bad possibilities, what is the probability that I get a bad event? It's the number of bad possibilities by total number of possibilities. The number of choices for S is the size of the family F. The number of choices for V is exactly the number of sets of size that much. which is U choose Q times U. Okay. So I have to bound the size of this band. Okay. And here's where we're going to use sort of like a computer science way of doing counting. Okay. I don't know if you've seen this before, but one way to count objects is to come up with an encoding and decoding scheme. All right. What does it mean? Okay, so we have to bound / count bad, right? So we want to count the number of things in this bad set. So the way we will do it is to use like an encoding scheme, meaning suppose I have some space, whatever that is. Let me call this G. Actually, let me just call this O, some space of objects. Okay. I have some space of objects and I have a map which maps from objects to L bits. All right. Is an encoding map. Okay. What does this mean? Encoding map means that it's a one-to-one mapping. Okay, so encoding means that it's a one-to-one mapping. Okay. What does this tell me about the size of O? If there is a map for encoding objects from my whatever O to using only at most L bits, the number of objects should be at most 2 to the L. Okay. This is what, just follows, because if it's a one-to-one mapping, then the pre-image must be at most the range. So size of the objects must be at most 2 to the L. Okay. And not only that, one way to prove that a mapping is an encoding is to, how can I prove that something is an encoding? You show that, okay, if there are two distinct objects, they map to 2 different outputs, or what's kind of a more, again, computer sciencey way to prove that something is an encoding? To decode. Okay. So if we have some encoding map and a decoding map such that decoding meaning, given the encoding, I can exactly reconstruct the original element, right? In particular, it implies this. Okay. So we'll basically construct an encoding and a decoding with few bits to count the number of these bad things. All right. Again, as I said, it's kind of a weird way to do the counting, but there are many cases in combinatorics and especially in CS where you do such an argument. Okay. All right. So let's take a 5-minute break because this encoding and decoding are very subtle. And when we come back, we'll do this encoding and decoding in one go. And as I said, this encoding and decoding is like 10 lines or maybe 20 lines of pseudocode, but it is subtle. So let's go over it slowly. And if something is not clear, please ask me. Okay. All right. Again, let's draw a picture. Right? So what are we saying? So we have these S1, S2, Sn. Right? This is V. So I have S1/V, S2/V, Sn/V. Okay. But then we're kind of building this minimal fragment map. There, right? So what does this mean? We might have something like this. This is its minimal fragment. Maybe for S2, we are mapping by meaning its minimal fragment is S1. It could happen, right? Maybe for S3, it's going here. This is going here. Something is going here. Okay, so this is M of S2 comma V. This is M of S1 comma V, and so on. Okay. The mapping, of course, you only look at the fragment, whatever is left uncovered, right? So in some sense, okay, so what's the intuition really? Okay, let's take some S comma V such that M of S comma V is big. Like these are the bad things that we're trying to count. Okay. What we're going to do is, instead of encoding S comma V, I'm first going to tell you what is this minimal fragment. I'm going to specify M of S comma V directly, this minimal fragment. Okay. Imagine you know this. Okay. The point is, if you know this, you gain more or the number of possibilities for S which map to M is much smaller. Okay, that's the win. Okay. So I know it's a very high level intuition. Hopefully it helps a little bit when you look at the code. So the intuition is, suppose we know M. Okay. Now then S must contain M. Okay. Right. That implies that S/M is contained in the link for M. Right. So the link of a set M is all the sets in my family which contain M, and then you take the difference. Right. And the big win is that the size of Fm is small. Okay. So far, I'm just going through the definitions, right? So why do I kind of win in some sense in the accounting? To specify S, I need to tell you which of my size of capital F many sets I am, right? That takes log of F bits of entropy. Okay. But if I know M, I only need to tell you which of these Fm sets I am. Okay. So I only need log of F minus S log M bits. Okay, so that's the win, really. Okay. It'll play out in the calculations, but I'm jumping ahead and saying the reason we win is because we have a spread family. Someone knowing a single element gives you more information about which set I could be than what I would have if I were not spread. Okay. All right. So at a very high level, to specify S directly takes log of F bits. if we know M to specify takes okay, because the size of the family has shrunk. And that's the win. This minus is what's going to really make our day. Okay. But anyway, so that's the intuition. So just keep that in mind. And somewhere that has to come into play, and it comes out to play in the encoding. All right. So what's the encoding map? The encoding map will have 4 components. I'm not going to write that in bits. We'll count the bits later on. Okay. So we have S and V such that okay, this is what we have. Now, to encode, we had to prove it's an encoding. We'll do that by decoding later on. I'm going to write down the following pieces of information. First, I'm going to write down Z, which is it is something. I'm going to specify what this set, which is a union of V and MSV is. I don't know what V is. I don't know what MSV is, so far at least. I know what their union is. Okay. Next, so maybe let's see. Okay, so well, okay. So let's define now. I'm looking at all things in my subset which are contained in this set C, right? So what does this mean? If you go back to this picture, I have these fragments, right? So let me maybe use this color. All right. So I picked, maybe this is the minimal fragment I'm looking at. Okay. Z is this union V. So all the pink region, right? Now, there are many sets whose which map to this. Okay, and that's what essentially F prime is. Look at all sets in my family whose minimal fragment is exactly MSV. All right. And that is what this guy is. Again, as I said, it's a sequence of definitions and things, but it's subtle to understand why it works. Okay. And note that F prime is not empty. Right? Because S itself is contained in F. All right. So now fix some S prime belonging to F prime arbitrary. Okay, it doesn't matter what it is, just has to be one guy. Okay. All right. So now comes the actual encoding. Okay. So the two things we need to do. First, most important thing is to show that this is a valid encoding, meaning we can reconstruct S comma V from this information and then do some accounting to decide how many bits you need to store these things. Okay. All right. So all right. So let's see, why is this an encoding? Any guesses? We'll work through it slowly, but we have to recover S and V, right? So why would this be in encoding? How can I recover S from this information? Bit from Z S prime M comma S M. How can I recover S? Well, S equals okay. So I wrote down a set which is contained in S and then the difference. So S equals M union S slash M. Right? Remember, M is actually the minimal fragment, so it is contained in the original set. Okay. Second one, how can I recover V? How can I recover V from this? Yeah. Yes, exactly, right? Because we know that M is disjoint from V. So when I take out M there, you are going to get back V exactly. Okay. So V is just Z slash M. Okay. And that's it. S prime is not playing too much of a role, but we'll see it's really there to help me count the bits in an easier way. All right. Okay. Because somehow yeah, we'll see why in a second. Right. So this is definitely an encoding because I can reconstruct S and V given those things. Okay, but now comes the real deal is to how many bits to write down encoding of S comma. Okay, so there are 4 components here, right? So I have Z, S prime, M, S, and M. S slash M. And there are 4 components. For each one, I'm going to count how many bits I need, right? And just do some kind of addition afterward, right? So let's do it one step at a time. And in some sense, we're not going to be too clever beyond this one thing. Okay. How many bits to write down Z? What do we know about Z? Z is a set whose size is right. So where did it go? Right. So size of V is Q times size of U. Okay. And this has some size, right? So all I'm going to use is that Z is some set whose size is Q times U plus size of M. That's it. So I'm going to write down the set exactly. So Z is exactly Q times U plus size of M, implies I can write it down with, or maybe I can just say implies number of options for Z is okay. I'm just writing down the entire set. All I know is its size. I'm going to write down one set. This might even be exact because I'm not using any other information. How about S prime? I know Z. How many bits do I need to specify S prime? Or is there any flexibility in S prime really? My claim is there's really no flexibility. It's a deterministic choice. It's a deterministic function of Z. If I know Z, F prime is uniquely defined, and this is the first set in it. So S prime is uniquely defined. Okay, so there's no flexibility in it. Okay, so the number, how many S prime, number of options is exactly one, because we already know Z. Right, so this is where kind of counting bits is helpful, because we're saying I know Z, so S prime is uniquely specified. I can kind of then infer S prime by myself without you giving me any more information. Okay, so it seems like S prime is redundant in some sense. So why was it helpful in the first place? It's helpful for what comes next. I have to specify M. Okay, it has some size. In the bad case, we have say, we're working in the assumption or implicitly with the assumption that this holds. Okay, so if I have to write down the set set M directly, then it's like you choose K over two options or something even worse. Okay, which is too much information. But the reason we win, or one of the things that we're going to exploit here, is that M is contained in S prime. Why? It's kind of by definition. Okay, and this is where the minimal fragment thing really shows up. And okay, so let's go to this picture. So what is f prime? F prime was saying, given this, look at all the sets which contain this guy, right? Now, since this is the minimal fragment, this should be contained in every one of them. Okay, so I don't have to, write down M from the whole universe. I know S prime, wherever that is going to contain M. Okay. So instead of writing down M as a set of size capital M from, whatever from the universe, I'm going to specify it relative to S prime, which I already know. Okay. So the number of options is okay. Instead of being size of the universe, it became size of S prime. Okay, which is basically, K choose M. And in some sense, we are even going to just approximate it as 2 to the K. Okay, you can, it doesn't matter. So I know that it doesn't matter, but you can be precise and then realize that it doesn't matter. All right. And finally, another big savings comes from the spreadness, which is how about S/M, right? So at this point, I know what M is, and I have to specify S/M, right? But to do this, I can go to the link of M, which is okay. So the number of options for S/M is okay. So if me box out what all things that we have. So I have this here. This is only 1. This is 2 to the K, an upper bound, and then we have this guy. Okay. Any questions about this? As I said, it's easy to follow when line by line, but it is very subtle in how you're exploiting spreadness and how you're exploiting kind of the minimal fragment nature. The minimal fragment nature comes from this observation. Okay. And the spreadness is this guy. That once I know M, I gain a lot of shrinkage in the number of possibilities for S because of spreadness. Okay. So this implies that the number of you have to multiply everything, so you get okay. And you can use some further simplifications, and this whole thing is at most times Okay, or this is really. Okay, why is this true? This is just some binomial approximation. You can work with the exact thing, but I can simplify it too. So like n, when I add a little bit here, I can bound the relative thing this way. Okay. So this comes from okay, this is true for the parameters that we have. It's just a binomial thing. I'm not going to prove it. Just take it for right. So I get I'm just separating out kind of the baseline that we had and that. Okay. All right. So now the final calculation is good to say, so how about the size of bad? Well, bad things are those where do you go? Yeah, here. Are those where the set had size at least k over 2. Okay. So we just have to sum this up. Is less than or equal to okay. And it takes some oh wait, I'm writing this wrong. This is s to the minus m. And so remember, spreadness means that every element I add gives me a hit of 1 over s, right? So that's why this is s to the minus m. Okay, so this is s to the minus m and s to the minus. Yes, I get q times s to the minus m. Okay. And you can work this out as okay. Now you're basically done. You have this guy, and we are looking at what s needs to be, right? So as long as as long as q is bigger than or equal to, let's say, 100 by s or something. Okay, if it's 100 by s, what do I get? It's like 100 to the minus m. I'm summing from k over 2 to the k. This 2 to the k will kind of basically also be absorbed in there, and you get the desired one. Okay. So think something like this. So as long as q is bigger than c1 over s for some constant c1, we get okay, maybe put 1,000. We are not worried about the constants. People have optimized the constant. The constant is actually not that bad. If you're really precise throughout, you can get a pretty small constant. Okay. Any questions? Right. So the big wins were in these two steps, the last C and D encodings. And so here, when we use the fact that use spreadness to say every element I get to know in my set S reduces the possibilities by 1 over S. If I knew M things, it became S to the minus M. Okay. So the minimal fragment is big. That means that the number of possibilities has shrunk a lot. Okay. And then here, when we said instead of looking over size of U, I can just look at subsets of a single set that I already know. Okay. And so this implies this guy, but this is exactly the probability as we stated, right? So all the way here somewhere we have it, right? So this is the probability. Okay. So implies the proof of okay. So let's just summarize what we did. We defined this notion of minimal fragments, which helped us really to kind of zero in on a definition which is minimally necessary to cover one of the sets in the family. I don't have to cover S2/V. If something is contained, I'm going to focus on this. If there's something even smaller than this, I should focus on that. Okay, that's what we were doing. And then we had this conclusion. Right. And once we have this, we can, of course, we're going to iterate what we have to do. So how do we finish the proof of the main spreadness lemma from this, right? This is just saying that a single set might cover half of them, but eventually we need to get to this statement, right? So this follows more or less by induction. I'm just going to do it. So define f prime equal all s such that suppose I pick a V, and now I'm going to look at a new family, which is all things without the where the minimal fragments are small. Okay. Now we're going to say that the next step is just to formalize the induction. It's a random set of size q times u, where q is greater than or equal to some constant over s. Then f prime as defined above Uh, okay, so what is this saying? Saying, my first set V covered some of these sets. I'm only going to look at sets where I've covered at least a half, right? So meaning uh, the minimal fragment sizes are small. So what is left to be covered is small, okay? And by a probability lemma, we know that most of the things, like with probability 100 to the minus k, you're 1 minus 100 to the minus k, you're kind of satisfying this, okay? So you can use that, this is just from definition. I'm taking out the fragments, and whatever is left is of size at most k over 2. The second one, it follows from that statement. You just have to do Markov inequality. It's like 100 to the minus k. I'm just making it 10 to the minus k and 10 to the minus k. So the size might drop, but only a little bit, okay? And then I might also lose something in the spreadness. How much do I lose? Basically this much, okay? I would lose a tiny, tiny bit in the spreadness, okay? Now, once I do this, I can apply induction on f prime. F prime is spread. So I'll say, okay, I'm going to pick another set. I'm going to cover k over 4 again. What's left is k over 4, okay? Proof of this. So, okay, proof. A is from definition, right? So if okay, because it's the minimal one, the original one must be uh, small 2. And what happens next is this is what we have. And then the size of f prime is basically from the probability. Okay, so and why is this true? This is basically because this implies that So each S is kind of bad with probability 100 to the minus K. So with over F over V, the expected size of F prime is this much. Okay. And now you can use Markov's inequality to say if something happens with like, 1 minus delta probability, then somehow with the expected size is like 1 minus delta, then the probability that it's more than like square root delta is like less than or equal to square root delta. Okay. So maybe another way to think about this is that this implies that it's a non-negative random variable. Now this implies that okay, so the gap is going to be small with high probability. All right, by Markov's inequality. Okay. So that takes care of this guy, and we have to argue about the spreadness. And the spreadness is again immediate because let's say I have F prime. It's a subfamily of F. I'm taking a collection of things there. And okay, this is true. And since F is a spread, I can say this is at most S to the minus I times size of F. Okay. And now this is S to the minus I times like, we know the size of F prime is big, right? So I get right. So more or less what it's saying is that I have a family which is spread. If I take a significant fraction of F, like almost everything, but drop a few things, I cannot destroy spreadness just because of that. Okay. And this is what we are going for, right? We're essentially taking the hit completely. Okay. Any questions about that? The last part is not the tricky part, it's just bookkeeping given the encoding and decoding lemma. All right. And finally, we can now use induction. Not induction, but just iterate the last two lemmas to get main spreadness lemma. Okay, and I'll leave this as an exercise for you, meaning just show that these two together imply the main spreadness lemma, which was this guy. Okay. And so the proof is just every time you cover half, eventually you'll cover everything after log k time. Okay. So let me not delve into that because it's mostly some, just making sure the induction kind of fits properly. But let me summarize with what we did. Kind of the big ideas, really. Okay, I'll say the first big idea was to define spreadness. Right? The definition of spreadness itself is kind of an important thing. And the first person kind of to do this was actually Talleyrand, who defined it in a different context for something about a conjecture in extremal combinatorics or probabilistic combinatorics called Kahn-Kalai conjecture. But it also has kind of its definitions in communication complexity and so on. In some I had a paper in 2015 in communication complexity where we defined some notion of entropy called blockwise dense entropy, which is exactly equivalent to spreadness, but just didn't show up there. Okay. And the next one is to not just look for sunflower lemma, but kind of strengthen to the robust sunflower lemma. Right, so here's where we got this sort of, take a random set, the chance that I'm going to contain something in the family is high. Okay. And this actually, you can phrase this thing that a random set contained in the family as the probability that a random assignment satisfies the specific DNF formula. And again, that has connections to computer science. And then once again, we had this notion of minimal fragments. And counting Okay. Finally, we had three proofs, three important ingredients. One, the definition of minimal fragments, which is kind of intuitive. What is the minimal thing that I need to cover to satisfy the robust sunflower lemma? Then we had this idea that, okay, instead of covering the whole thing, we're going to measure progress half at a time. Okay. Especially this is a technique that is useful when you're dealing with random sets. Because random sets have this property that instead of picking 100 elements at random, I can pick 10 elements, then 10 elements, 10 elements, and so on. And if I show that every time I make some progress, overall, I'll make enough progress. Okay. And finally, we had the counting by encoding. All right. So let me stop with that. And for the next lecture, we'll start a new topic. But before going there, maybe I'll hint at some of the follow-ups that have come up from these ideas, these three things. What other important results have been shown using this? Okay, so I'll briefly talk about them. We don't have too much time into covering them, but I'll just state a couple of very nice results, or at least the problems, and then move on to the next topic. Okay? All right, I'll see you on Wednesday.